In chapter one, we talked about just the basics of a statistical study and pretty much what that entails. Uh, in this chapter, in chapter two, now we're going to start talking about how to gather data together. Um, and then later on in chapter three, we'll talk even more about how to gather that data and analyze it further. But here, we'll start with what's called frequency distributions, histograms, and other related topics. There are basically three parts to this section. One of them is learning how to do a frequency table, how to do complete histograms, and then how to calculate cumulative frequencies using ogives. But with that being said, let's go on to the first part, which is our frequency table. So a frequency table partitions data into classes or intervals of equal width and shows how many data values are in each class. Or basically, a frequency table, when you hear the word frequency, it's very similar to the word frequent, meaning happening often. When we create a frequency table, we're trying to tally up how often a data appears in a specific group. So the way that the classes or intervals are constructed, they're constructed so that each data falls into exactly one class. Now, how much do you need? Well, usually 5 to 15 is a good range. If you use less than 5, you risk losing too much information. But if you use more than 15, then you risk having your data not being sufficiently summarized. So anywhere between 5 and 15 is usually a good mark to use. So here are the steps to create a frequency table. So first off, you want to determine the number of classes, and you want to calculate the corresponding class width. Now again, we said 5 to 15 classes are good, but what is the corresponding class width? Well, the class width is the value of the difference between the largest data value in the class and the smallest data value of that class divided by the total number of classes in the frequency table. So basically, if you want to calculate the width of your class, you take the largest data value in your set, and you subtract the smallest data value in that set, and you divide it by the number of classes that you want to have. And you always round up to the nearest whole number. Then once you have your width and you have the number of classes, then you create your distinct classes. So you always start with your lower class limit. So the smallest data value, use the smallest data value as your starting point. Once you get that done, then you want to add the class width to that number to get the lower class limit of the next class, and so on and so forth until you get the number of groups that you want. So let's say I want 7 classes. I start with my smallest value, then I add the class width until I get 7 different numbers. Those numbers are my lower class limits for each class. Then you want to fill in the upper class limits to create distinct classes that accommodate all possible data values from that data set. So before I go any further, let me go ahead and tell you what those are. Lower class limit is the lowest data value that can fit in a class. The upper class limit is the highest data value that can fit in a class. And then you also have what's called midpoint. The midpoint is the sum of the lower class limit and the upper class limit divided by 2. This is not to be confused with the class width formula. So if your class width, you take your largest minus your smallest of your entire set divided by the number of classes that you want. Midpoint for each class, you take the lower and upper limits of that class, add them together, divide by 2. So anyways, so if I have for my 7 classes, if I have my lower class limit, let's say my first 2 lower class limits are 1 and 7. Okay? Or 1 and 7. If 7's the lower class limit for my second class, it means that my first class has to end in 6. Because again, they have to have the same width and they cannot overlap. So then I fill in the blanks pretty much for that. I put 6 as my first upper class limit. Then I'll add my width to continue filling up that chart until every lower bound has an upper bound. Then you want to tally the data into the classes. This step is probably the most tedious step, especially if you don't have your data in numerical order, because you got actively searching for the data. So you want to tally the data into your classes. So each data value should fall into exactly one class, meaning that if whatever number I find, I figure out what class it's in, and I make that tally. And then the total amount of tallies for each class is called your class frequency. And then, of course, you want to compute the midpoint, which I just talked about. So add the upper and lower ends, divide by 2. Then determine class boundaries. Now, what is a class boundary? The class boundaries are the halfway points between the upper limit of one class and the lower limit of the next class. To calculate your boundaries, for your upper class boundary, you add 0.5 to your upper class limit. For your lower class boundary, you want to subtract 0.5 from your lower class limit. Okay. So basic frequency tables show how much of the data falls into each class. But also, it's useful to know the relative frequency of a class. Relative frequency of a class is the proportion of all data values that fall into that class. Think of relative frequency as like a percentage, right? How much of the data falls into a particular class. Now, to calculate the relative frequency for each one, you want to divide the class frequency by the total of all frequencies, aka your sample size. If you're working a problem that says to divide by your sample size, that's the total number of frequencies you have. So if you have all your tallies, you add up all the tallies from every single class. That's your total of all frequencies. Okay. Then for each class, you take that number, that frequency, divided by the total of all frequencies, and that's your relative frequency. And you always want to round to 2 decimal places when we do this. Okay. Anytime that you're working with a frequency table and you have the frequencies, the very first thing that I will always tell you suggest is to get me the total number of values in your table. How many data values in total are you working? Because that's definitely going to help you with this. It's also going to help you along later on. Okay. So for a relative frequency table, first you want to make a frequency table. That's obvious. Then for each class, compute the relative frequency f over n, where f is the class frequency and n is the total number of your sample size. Okay. So for example, if the first class frequency is 14 and the sample size is 60, then if I want to find the relative frequency of that class, what I want to do with that, so my relative frequency is going to be for that class is going to be my class frequency over the total number of data values. And I'm going to divide that up into round 2 decimal places. And I get 0.23. Okay. All right. So this is kind of an example of what a frequency table should look like. Here it looks like my class width is 8. It looks like my class width is 8. Okay? And then so starting with my smallest number, which is 1, we're adding the class width until I get the desired number of classes. In this case, it would be 1, 2, 3, 4, 5, 6. Okay? From there, that's when I fill in my upper limits. So if 9 is the lower limit for the second class, then 9 can't be the upper limit for this class. It has to be 8. Okay? And then, of course, plus 8, plus 8, plus 8, plus 8, plus 8, so that they all have the same width. Then I'll make my tallies. So that's how many times a data value appears in that range. There's your frequencies. That's the total number of tallies. And there's your class midpoint for each one. So for class midpoint, add and divide by 2. Same thing here. Add, divide by 2. Okay? And then, of course, you have your class boundaries. So for your class boundaries, again, for your lower ends, you subtract 0.5. For your upper ends, you add 0.5. And here's what your relative frequency table should look like. Again, there's my classes, and there's my frequencies, and I take each of those frequencies divided by the total number of my sample, which is 60. Now, the cool thing about relative frequency is, first off, we round to the nearest hundredth, which is 2 decimal places. The total of the relative frequency should be 1. So again, we're thinking of relative frequencies like we would percentages. If you calculate all the percentages in your sample, it should add up to be 100%. But because we're rounding, the rounded results may make the total slightly higher or lower than 1, and that's okay. Like 1.01 or 9 or 0.99, that's okay. Now 0.67, you got some work to do there. Okay, but if I add these up, start here. So 23 plus 35, that's 58. Then 76, 86, then 93, and then 1. So yeah, that does check out. Okay. Now frequency tables are useful, but sometimes you need visual aids. A lot of people are visual learners. That's where histograms come in. Histograms and relative frequency histograms provide effective visual displays of data organized into frequency tables. So in a histogram, so a histogram is a graph in which bars are used to represent each class. Now I know for each bar on that graph, the width of the bar is the class width, the height of the bar is the class frequency, and for relative frequency, the height of the bar is relative frequency. Okay, so here's how you make a histogram. First, you want to make a frequency table. Now, it always helps to include a relative frequency column in that table, in case you're doing both. All right, so make a frequency table with your classes. You want your class boundaries on the x-axis and your frequencies or relative frequencies on the y-axis. Okay? So here's how it's going to work. For each class of the frequency table, you're going to draw a bar whose width extends between corresponding class boundaries. So from one class boundary to another on the x-axis, that's where your bar extends. For histograms, the y value on that chart is the class frequency. For relative frequency histograms, the height is the corresponding class relative frequency. Okay. And there are different types of distribution shapes for histograms. So if the raw data comes from a random sample of population values, the histogram constructed from that sample values should have a shape that is reasonably similar to that of the population. If you take data from a sample and put it into a histogram, chances are the population might be the values that you would get from a population might be similar. Now there are different types of shapes of histograms. First, we have what's called a mound-shaped histogram. So a mound-shaped symmetrical histogram is one where both sides are the same when the graph is folded down the middle. So if I take a line, cut it down the middle, it should look almost reflective of each other. Then we have a uniform or a rectangular histogram. So in a uniform histogram, every class has the same frequency. Hence, every bar has the same height. So you could also say that a uniform distribution is a symmetrical one also. So you could say this can also be a symmetrical histogram too, but with the added caveat that the bars have to be the same height. Then you have what's called skewed left or skewed right. And a skewed left or a skewed right histogram, that's where the tail of one of the graphs either stretches out to the left or stretches out to the right. For example, here, this graph is stretched out to the left. That's a skewed left histogram. Here, the tail is skewed out to the right. It's called a right skewed histogram. And then, so of course, the direction of skewness is on the side of the longer tail. Okay. Then you have a bimodal histogram. So in a bimodal histogram, two classes with the largest frequencies are separated by at least one class. So the top two frequencies of these classes they don't have to be exactly the same, but they have to be the two highest. So notice how you have this gap here between your two highest frequencies. And here, you have at least one class separating them. Now, a way this might happen is it might indicate that you're sampling from two different populations. Like, for example, if you're trying to show the heights of random sample of adults, you might have a sample that comes from men and a sample that comes from women. This might be a case where you have a bimodal histogram. Okay? But we have to be careful for outliers. So if there are gaps in the histogram between bars at either end of the graph, your set might include outliers. An outlier in a data set is the data value that's very different from other measurements in the data set. For example, in a study of salaries of employees at a company, whose salary do you think could possibly be an outlier? Well, if you're looking at salaries of, like, say, a multinational corporation, the CEO or the owner might have a higher salary than, say, the janitor or an office worker or anything of that nature. Even the janitor salary might be an outlier also. Okay, I want to go back to the bimodal histogram for a second here. This is not the same as having an outlier. In a bimodal histogram, you have these two classes in this example separating your two highest. In a histogram that has an outlier, you might not even see a class there. It might be completely blank right here, blank space. So we got to watch out for those outliers. Those outliers can really mess up our histograms. Now for histograms and relative frequency histograms, here's what they tell us. They tell us if the data, how the data distribution looks. Is it symmetric? Is it skewed? Is it bimodal? Are there any outliers? Which data intervals contain the most data? How spread out is the data? And of course, outliers can help with that. Outliers kind of tell us about that too. Okay. Then we also have what's called cumulative frequency tables and ogives. So sometimes instead of relative frequency or even general frequency, we want to figure out cumulative totals instead of frequencies. So cumulative frequencies tell us how many data values are smaller than an upper class bound. So again, I'm gonna keep stressing this. You cannot do any of these things in this section without doing a frequency table. Once you have your frequency table, it's pretty much straightforward to get your column of cumulative frequencies. Here's the definition. Cumulative frequency for a class is the sum of the frequencies for that class and all previous classes. And of course, like frequency tables and relative frequency tables use histograms and relative frequency histograms. Cumulative frequency tables use what's called an ogive. An ogive is a graph that displays cumulative frequencies. So here's how you make it. First, you need a frequency table. Again, I can't stress that enough. You need a frequency table. Specifically, you need to show class boundaries and cumulative frequencies. Then, I'm gonna go ahead and switch these two because I believe this one should go first. So an ogive is different from a histogram in that it's a line chart instead of a line graph instead of a bar graph. So for an ogive, your first point on that line graph should be on the x-axis at the lower class boundary of your very first class. So your absolute lowest boundary is on the x-axis is where your first point should be. Then for each dot that you put, each other point that you put on your graph, the x values are your upper class boundary, the y values are your cumulative class frequency. And then of course, you want to connect those dots when you're done. So for example, Aspen, Colorado is a world famous ski area. If the daily high temperature is above 40 degrees Fahrenheit, the surface of the snow tends to melt and then freezes again at night. This can result in a snow crust that is icy and can increase avalanche danger. So here's an example of a cumulative frequency table. So here, I have my upper and lower bounds. So on my ogive, this is going to be the very first point on my ogive, this one right here. It's going to be on the x-axis. Then 20.5, 30.5, 40.5, 50.5, 60.5 with those corresponding frequencies, with those corresponding cumulative frequencies. So here, my first class is 23. That's my frequency. Anytime you do a cumulative frequency table, your first cumulative frequency should always be your first frequency. And then you keep adding frequencies as you go along. So 43 plus, anyways, so this plus 43, this plus 51, this plus 27, this plus 7. By the time you get to your last one, you should have the total of all your cumulative frequencies. That's why I mentioned, not just for relative frequency, but for cumulative frequency, it helps to total up all your data right away, because that's going to help you with this too. It reminds me of the game show called Chain Reaction, where you have your first word and your last word, you're trying to connect the two. So it kind of reminds me of that. Now, as far as the ogive goes, so again, you already talked about how to compute cumulative frequency, and then I'm going to draw the ogive. That's what the ogive for this graph should look like. Again, my very first point is on the x-axis at my lowest bound. And then for my first upper bound, frequency. Second upper bound, frequency. And then so on and so forth. So for example, looking at this ogive, estimate the total number of days with a high temperature lower than or equal to 40 degrees. Remember, past 40 degrees, that's the danger zone. But it looks like there are about 117 days out of 151 where the high was either 40 degrees or less than. So I would say it's a good majority of like almost like more than 2/3 of ski season where the weather was pretty nice. And so ogives again tell us because it's a diagram of cumulative frequency. It tells us how much of the data is less than the indicated value on the x-axis, and how slowly or rapidly the data values accumulate over the range of the data. Now, if you look back at the ogive, it looks like it has its highest frequency here, where it changes the most, from here to here, and this is probably where it changes the least. So you can also determine, where, like, what, which temperatures had the most increase in change.